Okay, so we just completed the fettuccine graphs, right? Let me remind you of what we did. And if you're watching the video, you can't see this part, but I can always show you later. So here's an example of a sine and cosine graph that was done. This is the circle that you used with your purple string to measure this out. I just cut the circle out. And so if I start at 0 here and I put this down on my x-axis, do you see how when I roll my circle, what's happening is I'm coming up with all of those x values that are marked on there, right? So we literally took the unit circle and unrolled it. Okay, then we had what kind of popped up off that x-axis was either our sine or our cosine values, but not both at the same time like they are on the unit circle. And we'll talk about the different kinds of equations that create, that link this to the circle later on, but we got to get this other stuff down before we can get that far. So anyway, this is your sine graph, this is your cosine graph. They look very similar to each other, yes? What could I do to the cosine graph to make it into a sine graph? What do you think I could do? Yep, just, right? Horizontal shift, that's it. How far would I have to shift the cosine graph to make it into a sine graph? Pi halves. If I just shift that over pi halves, it's going to look exactly the same, right? That's why graphs that have this nature to them, that, the up and down and up and down and up and down, are all referred to as sinusoidal graphs, even though they could be cosine graphs, because all cosine graphs can be made into sine graphs and vice versa. So you have things called sinusoidal functions, which you can kind of see like in a heartbeat and other things. In music, oh my gosh, they are everywhere, but they show up in a lot of things that we do. They're also what's called periodic functions because they run through cycles, and those cycles are called periods. So periodic functions are these kinds of functions as well. So this is going to go on page 104 and we're done. And so this is just a picture of what you did. It's not the same size because the same size wouldn't fit on here, but just so you can see that again, with the unit circle, your x is cosine, your y is sine, but we're graphing this. This is not a function, right? This is a circle, it's not a function. So when I unroll it and make them into functions that we can use, then that's when they look like our sine and cosine graphs, okay? So for parent functions, starting with sine, f of x is equal to the sine of x. My input is x, which would be an angle measure. My output is the sine value of that angle, okay? Same asking you at the door here. What's the sine of 0? No, 0. The sine of 0 is 0. What's the sine of pi? 0. What's the sine of 2 pi? 0, because your back is 0, right? What's the sine of negative pi? 0. What's the sine of negative 2 pi? 0. Well, there are all your x-intercepts right there of the sine function. The pi halves, pi 6, pi fourths, pi thirds, those y'all finally kind of got down pretty good, but 0 and pi halves keep throwing some of you off, and you have to kind of visualize those ordered pairs. After you understand the graphs, to me, the graphs help me with those more so than the unit circle does. Because if you know what the parent function of sine looks like, clearly the sine of 0 is 0, right? And that's no big deal. The sine of 2 pi and the sine of pi halfway, that sort of thing. So this gives me all of my x-intercepts. Well, not all of them, but all of them that I have graphed here. Now, this can go on forever in either direction, right? So how many x-intercepts do I have? An infinite amount, right? So when it's asking me for my x-intercepts, I don't have enough room to write out an infinite amount. So let's think about how we could talk about those. We actually want to talk about them as zeros and not as x-intercepts, so we don't have to do ordered pairs, so I should have changed that to zeros. So my zeros, they happen how often? How much? Every pi. It's starting at 0, right? Or but 0 is included in there, right? So could I say maybe my zeros would be like n times pi? Does that make sense? What would n have to be? Has to be a real number. Could be, has to be a whole number, right? Because I can't say 0.5 pi because pi halves doesn't include. But if it's a whole number, then I'm good. It could be positive or negative, and I got to include 0, right? So I need to say that n times pi to specify that it basically has to be a whole number. So I need to say that n has to be an element of the whole numbers, and to show that they're whole numbers, it's like a weird W where two of the lines are doubled. So you learned way back when about whole numbers, natural numbers, integers. I mean, I don't know how often you or how much you did with those things. I don't know that you ever learned the symbols. You may not have. But this is what, and I picked this particular picture because you can see it. Then because of this bad pixelation, you can't actually see it. But you've got rational numbers, integers. So with the integers, the Z thing is doubled right there. And then the W is like doubled right there. It's like a fancier one. It's not italicized. It's just that some things are doubled there. But our integers are positive and negative whole numbers, but you don't include 0. Okay, so that's why we have to call them whole numbers and not integers right there. That's where that comes from. But these are like your little number families. So integers is a Z, rational numbers is a Q, natural numbers are N, but whole numbers are all of your counting numbers, positive and negative, basically. So back over here, we've got, so once we have this, we've got all of our in there. Oh, we can also do our 0. When classes and intercepts, it's an ordered pair, right? Okay, so back up here, thinking about our unit circle, what does the sine of pi halves? 1. Okay, sine of pi halves is 1. What's the sine of 3 pi halves? Negative 1. So what's the sine of negative pi halves? Negative 1, because negative pi halves is the same as 3 pi halves. And then negative 3 pi halves would be 1, because it's 3 pi halves. So I've got my x-intercepts, I've got my max and min points, right? I could graph some of the other ones, but it would require me to estimate, and that's just necessary. This is enough to get the curve of the function, to sketch my parent function. And it looks something like this. And arrows on the end, because it's going to keep the repetitive period thing going. So our domain, well, it's going to keep going, so it's negative infinity to infinity, right? I never include my infinities. The range goes from negative 1 to 1. I'm including both of those because those are sine values that I get, right? Do I have any asymptotes? No. And this is on here because sometimes people want to say it's at 1 and negative 1, but it's not. Because think about a parabola. Just because a parabola has a minimum, there's no asymptote there. An asymptote is something that you're approaching, not something that you just keep bouncing off of unless it gets closer and closer, which it doesn't. So there are none. Okay, so your amplitude, this is a new word here. It's basically, it's kind of like the height, I guess you could say. Technically, look at the definition tomorrow, it's half the distance between the max and the min points. If you're talking about the parent function, it's the distance, or even if there is no vertical translations, then it's the distance from the x-axis to the max or the min. But in this case, that's 1. From negative 1 to 1, that's 2, so half of that is 1. That's kind of how tall it is. The period is the length of one cycle. So what was the length of one cycle? 2 pi. And I saw a really great way that somebody was doing it. I think it was Arian, so I'll give him props. He had a string, right, that you had wrapped around the circle, so you know the length, not the length of the string, but the length of from the beginning to wherever you hit 2 pi. The length of this is 2 pi, right? That is the circumference. Then he laid it out right here. It should be right there. That's the length of the cycle. It's actually 2 pi. This is what got wrapped around your circle there. All right, so our transformations looks like this. F of x equals a times the sine of b times x minus c plus d. That's if everything's thrown in there. You're not always changing everything though, right? That should look very familiar to you, right? With all of the other transformations that we did, it just didn't have sine in there. We would have said like f of there or whatever. That could be absolute value, whatever it is. It's all the same stuff here. Okay? The terminology changes a little bit because it's trig, but it's still the same stuff. If you could transform other functions, you can transform these. It's the same thing. Okay? Amplitude. The amplitude is basically how tall it is. So that's going to be like your vertical stretch. What affects the vertical stretch in transformations like this? A, right? This is your vertical stretch. It's what's multiplied out front here. So this is the absolute value of A, because we don't care about the sign there. The B is your horizontal stretch or compression, right? So basically what we think about with the trig stuff then is, well then what's the length of a period? Like the length of the period changes. And that's what that means. That's why it says period instead of horizontal stretch and compression. So if a normal period is at 2 pi, then I've got to figure out what I'm going to get if b is happening. Well, x lies, right? So if that b was a 3, I'd actually divide by 3, right? I wouldn't multiply by 3. So I divide by 3. So I need to take that 2 pi and divide it by 3. So it's going to be 2 pi over the absolute value of b. X lies. Okay. All right, and then horizontal shift is now called a phase shift, but it's the same as your horizontal shift. So what letter is that? Horizontal is D, yeah, and vertical is D. So that C there, and it's minus C, so X still lies just like before, okay? It's telling the same lies it's told before. Everybody good so far? All right, let's look at cosine. So f of x so what is the cosine of 0? 1. What's the cosine of pi? Look at your circle. You're over here. Negative 1. Cosine of negative pi? Negative 1. And cosine of negative 2 pi? 1. You know the shape. If you can picture the shape of a sine or cosine graph, it's going to help you with those zeros and ones and get them in the negative and positive, get them in the right spots. Okay, so that didn't help me with my x-intercepts at all, though. So that's where that pi halves. What's the cosine of pi halves? 0. And 3 pi halves is 0. And then negative pi halves and negative 3 pi halves, all zeros. Right? So those are real easy ones to graph. And then I'm just going to sketch in the curve. So, okay. So it has the same domain. Now, think of any cosine graph can be or the parent function of a cosine graph can be shifted over to make the parent function of a sine graph. Then aren't the domain and the range going to be exactly the same? Yes. Negative infinity to infinity. Range is negative 1 to 1. Now our x-intercepts, which we'll call zeros, actually change. And I don't get to do, it's not pi, n times pi. Where do we start? We don't start at pi, we start where? Pi halves. So it's n times pi halves. I can't say n is an element of the whole numbers because I don't want to include 0, right? So it has to be an element of the integers, and the integers is the funky z. But don't worry, when we're graphing, you're not going to have a whole lot of questions about the zeros where you have to state things like that. I just want it here at least on your parent functions so that you have seen it before. And those are things that you have to be able to speak about. What's your y-intercept? 0, 1. Oops. We have no asymptotes. Amplitude is still 1. Period is still 2 pi. Transformations. So f of x is equal to a times the cosine of b times x minus c plus d. Your amplitude, still your vertical shift. I'm sorry, your vertical stretch, rather. So it's the absolute value of a. Period is the same. All of this stuff is the same as it is for sine. Okay. Any questions at this point? All right. More about it. I just wanted to make sure we got it tied to why in the world we even did what we did over there. Because you should be able to take one of these, the same size, and take your little pieces of fettuccine off there, because it would be the correct